Hello, this is Professor Kevin Mark, Chapter 7, Periodic Properties of Elements. So in the 1860s, scientist Dmitry Ivanovich Mendeleev created the first periodic table based on atomic masses. So here he used chemical properties to put the elements in a table. And when he actually created this table, there were actually at the time blank spaces that he left in because he knew based on trends that eventually these elements would be discovered and were placed based on things such as their chemical characteristics, the number of protons, etc. As we know, we talked about the rows going from left to right, periods, and we have columns up and down. The main group elements, group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, etc. Those are the main group elements. We have alkali metals, the first group, alkaline earth metals in the second group. We have chalcogens here, halogens, and noble gases for group 8A. And again, transition metals in the middle. Valence electrons are the ones located on the outermost shell, the outermost electrons, another way you can say, as opposed to the inner electrons, which are found inside on the inner shells, not the outermost shell. So we say valence electrons are the ones that are the most important in the chemical reaction. They're the ones that actually transfer or share. They're the ones that give the element its property. So valence electrons we refer to a lot. Chlorine has 7 valence electrons because it is in group 7A, just like sodium has 1 valence electron because it has 1 valence electron and it's in group 1A. And there's no trend in the middle for transition metals in terms of valence electrons and what group. Effective nuclear charge, the Z effective, is the charge felt by valence electrons. So we have the nucleus, which is a positive charge, and the effective nuclear charge is how much the outermost electrons, the valence electron, feels that positive charge. So the analogy that I use here is with the person, for instance, an outermost electron, the person outside here, how much he, in this case, feels the fire. And we have these inner electrons here where the people are blocking some of that flame or some of that energy from the middle. So the equation we use, we will not do any calculations, but it's the Z effective. Again, how much this outer electron, this valence electron, feels the nucleus. So we have the Z, which is the atomic number, how much charge from the nucleus, and this screening constant, the effect from the inner electrons. So we talked about sodium. It has 11 protons and 11 electrons. The electron configuration, which we can talk now, is 1s2, 2s2, 2p6, 3s1. So we have 1 valence electron because there's 1 electron on the outer shell. And this is shown here. It's a nice picture, but for sodium, we have 11 electrons. So say this is the nucleus. We have 2 electrons, followed by 8 electrons. 8, E stands for electrons, and we need 1 more on the outer shell. So 1 valence electron for sodium, and we say it's in group 1A alkali metals. So as I just said, there are 10 core electrons, 10 in the middle, and we have 1 valence electron. We can also say the 1 valence electron is shielded by the 10 inner electrons. It blocks, we can say it blocks some of the positive charge in the nucleus. So a question to you, for helium, which has 2 electrons in the 1s orbital, would it take more energy to remove the first or second electron? So I'll draw for you. If this is helium, so it has 2 protons in the middle, and we said it has 2 electrons. So we have 1 electron here, and I'll draw the other one in red. So we have 2 electrons. So the question is this one versus, again, it's 2 protons. If it doesn't have 2 protons, it's not helium. So let's say we remove one of the electrons, and now we only have 1 electron. So the question is it easier to remove, I'll just say the one on the left or the one on the right? It would take more energy to remove the second electron. Why? Because there's no shielding effect from the yellow electron. The yellow electron is gone. So in terms of there's some little bit of shielding, a little bit of overlap as it goes around the proton. 2 protons, there's also no repulsion between the 2 electrons. As we recall, electrons, they don't like each other. There's some repulsion there between the two electrons. So those are the 2 effects that show that the right one, the electron here on the right, takes more energy to remove than the electron here, I would say the yellow one on the left. So the answer is the second one. So the 2s subshell is lower in energy. So if you remember, we have 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s2, 3p6. Again, this is an energy versus the distance away from the nucleus. So we know that the electrons fill up in the 1s first. That's why we have a 1s2. And the question is, why is this 2s lower in energy than the 2p? So this is a graph which shows the radial electron probability, the probability of finding the electron in the nucleus versus the radius away from the nucleus, going away from the nucleus. And we see here for the 1s, as we can imagine, it's very close to the nucleus, seen here. High probability of finding the electron very close to the nucleus. For the 2s and 2p, we stated in the previous slide that the 2s is closer in general, lower in energy. And we here have the yellow 2p and the 2s. So yes, in this case, if we were just to look at these 2 humps, larger humps, that yes, the 2p is closer. However, we have this small bump here in the purple, which tells us overall, when you put the 2 together, when you integrate and put the 2 together, that the 2s will be closer to the nucleus than the 2p. And this is a picture here that shows, yes, you have some electron density closer to the nucleus for the 2s, and you have a majority here on the outer here, around 288. So overall, the 2s is less shielded by the 1s core electrons than the 2p. And therefore, the 2s is lower in energy and more strongly bound to the nucleus. So we want to continue and talk about the Z effective. So for the remaining part of the chapter, we're going to focus on trends, meaning, if we go from left to right in the periodic table, if we go up and down or down or right, how does that affect the Z effective? So you can either memorize the trends, or more importantly and better yet, you should try to understand why, as for instance, as you go from left to right, the Z effective increases. So I'll draw a periodic table here. And let's compare. So it says here that as you go from left to right, the Z effective increases. So let's focus on sodium. Let's say sodium here. And if you go across, we have here argon. So let's compare sodium and argon, both on level 3. So if we look at sodium, how many protons? 11 protons. Argon, 18 protons. And let's just draw the levels. So we have for the sodium, we have 2 electrons live here, followed by 8 electrons, and we have 1 valence electron on the outside. So we have 1 valence electron. I'll put this in yellow. 1 valence electron. If we compare this with the argon, argon has same thing, 2 electrons on the first level, 8 on the next level, and draw the other level here. On the third level, we have 8 valence electrons. Put this in yellow. We have 8 valence electrons. So the question is, do these 8 valence electrons have a higher Z effective or this 1 valence electron? Remember, Z effective, we focus only on the outer electrons. Well, if we look at the two, sodium and argon, the major difference is the number of protons. So sodium is less powerful in terms of positive charges versus argon. Argon has 18 protons, sodium has 11 protons. The amount of shielding electrons, inner core electrons, is the same for both cases. We have 10 for the sodium, the ones on the inside. We also have 10 for the argon. So the only difference between the two is the protons, 11 versus 18. So my reasoning is, as you go from left to right, the outer electrons from the argon will pull in more because there's a stronger positive charge in the middle. They have the same number of shielding electrons between sodium and argon. However, there's a stronger pull from the argon. Therefore, the Z effective will be greater for argon than in sodium. So as you go from left to right, the Z effective will increase. The next trend for a given group, so as you go down, the Z effective increases, and this is just slightly. So if we compare, let's say, our periodic table again, let's take a look at lithium, and we can compare, for instance, cesium, Cs. So it states here, as you go down, the Z effective increases. So you have two effects here. You have the number of protons increasing as you go down. So I'll just write the protons increases as you go down. However, there are more shielding electrons as you go down as well. So I'll say the shielding electrons increases as well, the number of shielding electrons. So the number of shielding electrons increases, the number of protons increases. Those two counter each other. However, there's a stronger effect from the number of protons taking effect, because with the shielding electrons, as you go away from the nucleus, the shielding electrons have a smaller effect because the distance between the shielding electrons increases. So yes, you have a stronger effect as you go down. The positive charges increases as you go down. Yes, the shielding electrons increases the number of shielding electrons increases. However, that shielding decreases because of the spacing between the shielding electrons, therefore making it less effective. So cesium would have a larger Z effective compared to lithium. So the next trend we're going to talk about is for atomic radius, which tells us the size of the atom. So the general trend is as you go down a group, the atomic radius increases as you go down a group, and that hopefully is straightforward. As you go down, let's compare, for instance, nitrogen versus arsenic. Arsenic will be larger, have a larger atomic radius, and that makes sense from our talk in chapter 6, where you have 2p, 1s2, 2p, level 1, 2p, we have 3p, and the arsenic is located on the 4p. So as the number gets bigger, the quantum number gets bigger, the principal quantum number gets bigger, 2p, 3p, 4p, the size of the atom gets larger. The second trend here, it decreases as you go from left to right. And we can look back at our Z effective trend. If we again look at sodium versus argon. So again, I'm just going to focus on the valence electron. So that's one valence electron. If you recall, there's 2 on the first level, then 8, and then 1 on the outside. Here there are 8 valence electrons for argon. And I'll just write in yellow, there are 10 shielding electrons. There are 10 shielding electrons. So again, the major difference is there are 11 protons for sodium, 18 protons for argon. So again, there's a stronger pull from the argon. Same number of shielding electrons, therefore the stronger pull will bring in these 8 electrons closer to the nucleus. So they'll bring in, therefore the argon will be smaller than the sodium. So question for you, pick any 4 elements. I'll just give you 4. I'm just going to go lithium, carbon, chlorine, and let's say calcium. And my question to you is, put these from, we can go largest to smallest. So from largest to smallest. So I'll give you guys a minute to try. To small. So first you have to locate where these are on the periodic table. Calcium has 20 protons, chlorine has 17 protons, carbon has 6 protons, lithium has 3 protons. So the largest one would be calcium, because it's on the 4s level. So calcium would be the largest, so I'll just call this number 1. The second largest one would be, I believe, chlorine, because it is on the level 3, the 3p. And we have now lithium and carbon. Both of them are on level 2. So if you remember the trend, as you go from left to right, the atomic size, atomic radius will decrease as you go from left to right. So the next biggest one would be lithium, and the smallest one would be carbon. And here's a picture to show you the size. As you go down, the atomic radius increases. As you go from left to right, the atomic radius decreases. In terms of cations and anions, if you recall, cation is when you have a positive charge, and anion is when you have an overall negative charge. So if you compare two elements, for instance, sodium versus sodium plus. For sodium, which will have 11 protons, so 11 protons, therefore 11 electrons, 2 electrons again, followed by 8 electrons, followed by another 1 electron. Let me put this in green. So we have 1 electron. And if we compare that to sodium plus, what happens here? The amount of protons stay the same. Sodium stays with 11 protons. However, the amount of electrons changes. So we still have 2 electrons here, and we have 8 electrons. We've lost an electron. That's why we have a plus sign. So the question is, which one is smaller? In this case, the cation, Na plus, will be smaller because we've lost an electron and we're left with a lower level in terms of valence electrons. So the sodium plus would be smaller. And conversely, for anions, if you add an electron, that will be the anion will be larger than its parent. Isoelectronic, I mean iso means the same, and the number of electrons. So when two elements or ions have the same number of electrons, the same electron configuration, they'll have similar chemical properties. But the trend is, for a given set of isoelectronic elements or ions, so meaning they have the same number of electrons, the ionic size decreases with an increase in nuclear charge. So let's look at our example here. We have O2 minus, F minus, Na plus, Mg2 plus, and Al3 plus. All of these have the electron configuration, let me write, 1s2, 2s2, 2p6. Okay, so all of these have the electron configuration 1s2, 2s2, 2p6. What is the difference in all three of these cases? The amount of protons. So aluminum has 13 protons, oxygen has 8 protons. So you can imagine the Al3 plus will be smaller, shown here by 0.068 angstroms, because the more protons will pull in the outer electrons to make it smaller. Let's try the problem here. Sorry, and the largest one will be oxygen. It has the least number of protons, and it has angstroms, 1.26 angstroms. So arrange the following in increasing size. So I want you guys to give it a try. All of them are isoelectronic, so they have the same number of electrons. So we have to differentiate all three by the number of protons. So calcium has 20 protons. S2 minus has 16 protons. Potassium has 19 protons. In this case, chloride has 17 protons. And argon has 18 protons. So as we said, if we have more protons and they're isoelectronic, the ones with the most protons will pull in the electrons more. So Ca2 plus will be the smallest one, and the largest one will be the sulfide. Another property, ionization energy. It's the energy needed to add it to the atom to remove an electron. the valence electron. So this is the general equation. We have the energy added to an atom gives us the atom a plus charge state because it lost an electron, and the electron has left. So these are endothermic reactions because you need to add energy to the atom for it to lose an electron. And we use the term I1 as the first ionization energy to lose the first electron. The second ionization energy, I2, is the energy needed to remove the second electron. And we'll talk about that in a second. So as I just said, for the second ionization energy, here we have the the atom plus the cation, meaning the first electron has been removed. And then this is the equation, again, another endothermic reaction to show the energy needed to remove the second electron from the atom. So some general notes: the greater the ionization energy value, the more difficult it is to remove an electron. This is also shown here. The I1 is less than usually in general than the I2 and the I3. This is for a given particular valence shell or valence electrons on a particular level. And this is so because, again, the amount of protons stays the same. However, you have less electron repulsion between electrons on the same shell. If you have less repulsion, therefore it is more difficult to remove an electron from its outer shell. However, there's a point where you're going to remove all the electrons, and at that point it takes a great deal of energy to remove the next electrons because all of the shell is happy. So if you have a noble gas, those are not reactive. Those shells are filled. Noble gases have a very high ionization energy. It takes a lot of energy to remove an electron from a noble gas. So the general trend, as you go down a group, the ionization energy decreases. As you go down a group, the ionization energy decreases, and as you go from left to right, the ionization energy increases. So as you go down a group, this kind of couples with the effective nuclear charge, the Z effective. We said here, as you go down, the amount of protons, yes, does increase. However, we have the valence electrons being further away from the nucleus. So if it's further away from the nucleus, even though you have more protons, you have the shielding electrons, which inhibits some of that energy from the nucleus being felt. It's actually easier to remove the electron as you're further away from the nucleus. As you go from left to right, the ionization energy increases. So this also relates to Z effective because the effective nuclear charge decreases as you go from left to right, meaning that the electrons in the outer shell feel the nucleus less as you go from left to right. There are some caveats to this over here and between the N and the O and the beryllium and the boron, and we'll discuss this later. The question to you, which atom has a smaller first ionization energy, the carbon or the oxygen? So we can look here on our table here, and we see that the carbon is less than the oxygen. So you can either understand the trend or you understand why that's so in terms of the Z effective. So as I just said, there is a caveat or some exceptions to the trend as you go left to right, increase. There is an exception between the boron and the beryllium. If we look at the electron configuration for boron, it's 1s2, 2s2, 2p1. And if we look at the beryllium, it's 4 protons, 4 electrons. 2s2, sorry, 1s2, and 2s2. So the boron in this case will have shielding electrons, 4 shielding electrons versus 2 shielding electrons. So therefore it will be easier to remove the electron from the 2p1 instead of the 2s2. We also have another exception here with the oxygen and nitrogen. The oxygen has a lower ionization energy than the nitrogen. Let's look at the case for the orbital diagram for oxygen. We have 1s2, 2s2, so 2s2, and the 2p4. So put in the arrows, 1, 2s2, 2p4, 1, 2, 3, and I'll do the other one, the fourth one here in yellow. And we compare that to nitrogen. The nitrogen is 1s2, 2s2, 2p3. So we'll go 1, 2, 3. So the question is, it is easier or lower ionization to remove the yellow one for oxygen. Why is that? Well, we have 2 electrons in the same orbital. They will have some repulsion there. 2 electrons living together, 2 people living together, sharing the same bathroom. They'd rather have their own. That's the analogy I always use. But in this case, there's repulsion there. Therefore, it's easier to remove the electron from the oxygen valence electron shell. We also have a going down a group. The ionization energy decreases as you go down. So the atomic radius increases as you go down, as we mentioned earlier. The valence electron is further away from the nucleus, therefore less energy needed to remove the electron. And I spoke about this in the previous slides, about this trend. So I'll give you a try. Which has a higher first ionization energy, calcium 2+ or the Cl-. These two are isoelectronic with argon, so they both have the same electron configuration as argon. So it's 1s2, 2s2, 2p6. The major difference between these two is they have different number of protons. The chlorine has 17 protons. The calcium has 20 protons. So you can imagine it is more difficult to remove the electron from the calcium because of the more positive charge. They both have the same shielding electrons. So calcium 2+ will have a higher first ionization energy. Which has a higher second ionization energy. So lithium is normally 3 protons, so we remove 2 of them, or sorry, we remove 1 because the first ionization should remove 1, so therefore we have 2 electrons here versus a beryllium, which normally has 4 protons, 4 electrons. We remove 1 of the electrons, therefore now we only have 3, so 2 on the first level and 1 on the outside. So comparing the two cases, the second highest ionization energy will revolve with lithium because of the shielding effect from the beryllium. So there's shielding electrons here for beryllium, which will reduce the field from the nucleus. Therefore, the beryllium will be lower and the lithium will have a higher second ionization energy. So for electron configuration of ions, this is a different topic. Normally we do, without ions, we have the 1s2, 2s2, 2p6. But if we, for instance, have lithium plus, which means we've lost one electron, we would say 1s2. Normally it would be 1s2, 2s1. However, we've lost an electron and we lose it from the outer shell, the 2s, so the electron configuration of lithium plus is 1s2. In the case for iron, we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 1, 2, 3, 4, 5, 6. When we lose two of those electrons, it actually comes off the 4s. So the 4s2 will be removed. The electrons from here will be removed. And for transition metals, I don't want to go into too much detail, but when you add electrons on the transition metal, the 3Ds, the actual levels between the 4s and the 3D actually start to move, the energy levels, to the point where the 4s will be higher than 3D. So the 4s will lose the electrons first when you remove them from the iron 2+. The electron configurations for anions, adding electrons, the electron is added to the lowest empty unfilled n value. So normally for chlorine, it's 1s2, 2s2, 2p6, 3s2, 3p5. But when you add an electron, you add it to the lowest unfilled n value, which is 3p6, and this Cl minus will have a isoelectronic configuration with argon. I want to give you guys a try. Write the electron configuration of iron 3+ and sulfide S2-. So we can pause, I'll give it a try. So for iron, normally it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. However, it's 3+. The question is 3+. So we remove the two electrons here. And we also remove one here from the 5. So from the 6, it becomes 3d5. So the electron configuration for iron 3+ would be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. In the case for S2-, normally it's, for S, -2, normally it would be 1s2, 2s2, 2p6, 3s2, 3p4, and when we add two electrons, because it's 2-, we add two electrons, this will become 3p6. So another characteristic is electron affinity, which is the amount of energy that is lost or gained. In this case, lost, it's an exothermic, the amount of energy lost when you gain an electron. So as you can imagine, fluorine or chlorine, those have high electron affinities. They want electrons to make 8 because they already have 7, so they want another electron to make 8 to have a noble gas configuration. Conversely, versus sodium and lithium, these do not want electrons. They rather give up their one electron in their outer shell, so they'll have a stable valence electron shell, the following valence electron shell. So noble gases, they do not want any electrons. So they'll have a low electron affinity as you go from left to right. So again, sodium has a low electron affinity. Going to the right, chlorine has a high electron affinity. It wants the electrons, but immediate drop to argon, which is the noble gas, it doesn't want any electrons at all. And there's no trend going down a group. So I just said, as you go from left to right, the lithium, in this case, has a low electron affinity versus the fluorine, which has a high electron affinity. It gives up a lot of energy to get the electron. The noble gases, they don't want any electrons at all. In fact, their values are greater than 0. So as you go across, as I just said in the previous slide, the electron affinity increases. We also talked about nitrogen here. If you look at the orbital diagram, it doesn't want an electron because it's very difficult to put another electron in here due to electron repulsion. So it doesn't want an electron there. So a review, effective nuclear charge, as you go down, there's an increase, but slight increase. Going left to right, there's an increase in effective nuclear charge because the amount of protons increases. The shielding electron stays the same. This kind of corresponds to the atomic radius. As you go down, 1s, 2s, 3s, that increases the size of the atom. Going left to right, the atomic radius decreases because the effective nuclear charge increases, so it brings in the electrons from the valence electron shell closer. The ionization energy, as you go down, it decreases, and as you go from left to right, the general trend increases. There are some exceptions, such as beryllium and boron, nitrogen and oxygen. For electron affinity, going down, there's no trend, and going from left to right, it increases. Looking at, for instance, fluorine, it wants an electron to make 8, versus lithium, it doesn't want 7 more to make 8. It would rather give up its 1 electron.